The essential question for this video is, what are the properties of a dilation? Now, if we haven't defined dilation yet, we will be doing that soon in the videos and in class. But basically, class, a dilation is this. It's a procedure that allows us to take a shape and actually enlarge it or reduce it, but the shape itself stays the same. So a dilation is going to create a similar image. It's going to make it bigger or smaller, but it's not going to change its overall shape. Now, before we talk about dilation, I want to define something for you, something you should have seen last year, but just in case you don't remember it. It's this idea of prime notation. So write this description down, or definition of prime notation. It's a way of mapping corresponding vertices to identify the pre-image and the image. The pre-image and the image. A way of mapping corresponding vertices to identify the pre-image and image. For example, if the vertex of a pre-image is A, the corresponding vertex of the image would be A prime. And this little mark here, it kind of looks like an exponent of 1, but it's not straight up and down. But just want you to see this is not A to the first power. This is A prime. We'll see how this plays out in our example of properties of a dilation. So on your paper, you've got two triangles. I want you to take your ruler or a straight edge. If you don't have one, please use one. And I want you to draw a straight line through the top two vertices, and you're going to draw them carefully and then draw them down toward the end of your paper. And when you do that, if you do that again for the next two corresponding vertices, and then the bottom two corresponding vertices, what you're trying to do is draw them all so that they all actually meet at one point over here. So let's go ahead and pause the video and get that done. And then once you get that done, let's label a few things. This point right here is called the center of dilation. You dilate two shapes, you'll always have a center or a point that you're dilating from. So to change this smaller triangle to this bigger triangle, we use the center of dilation to actually get that triangle to grow in size, but not to change its shape. And I'm going to use a different color here. Let's label that point as D. Alright, in fact, let's label the rest of the points here while we're at it. So let's make this one A. Now here's where our prime notation comes in. If this was our starting triangle, let's actually label that as pre-image, or PI for pre-image. There's our starting triangle. If that triangle is being dilated from the center of dilation and it's becoming a bigger triangle over here, our corresponding vertex we're going to label A prime. And then this one, if this started off as B, we're going to call this vertex B prime. It's kind of like A copy, B copy. It's the copy of B, the copy of A. And then if we label this one as C, we're going to label this vertex as C prime. So there's where we use prime notation. With prime notation, it's nice that you match up the letters from one triangle to its dilated triangle. In this case, let's label this one as image. Pre-image, if we haven't covered it yet, you will be covering it. Pre-image is the starting shape. Image is the copy or the ending shape after the dilation. All right. Let's go ahead and put a few more values on here. Let's label some sizes. We'll be using these in our descriptions. Let's say that A prime, C prime is 10. We're not going to put a unit of measure here. Let's just put a number. And this is 5. And then let's say that B prime, C prime is 8, and this is B, C is 4, A, B is 3, A prime, B prime is 6. And then let's label a couple more things. The distance from A to A prime, let's label that a different color. Let's say that's also 6. And let's say from D to A is also 6. So there's all of our measurements that we're going to use for our discussion. Okay, so we've got our center of dilation, our pre-image, which now has been blown up or made bigger into our image. And let's look at all of the properties that this creates by using the dilation rules. The first thing is, a dilation always has a center of dilation and a scale factor. Always has a center of dilation and a scale factor. That means you can always find a point on the grid or a point on the paper where one shape turned into the other one, and all the corresponding vertices intersect at one point. The next thing we know is that if you have a dilation, corresponding angles are going to be congruent. That means in this particular situation, we know that angle A is going to be congruent to angle A prime. Angle B has to be congruent to angle B prime, and angle C has to be congruent to angle C prime. If you're using dilation, that's automatically going to happen. You're going to end up with congruent corresponding angles. The next property is corresponding sides are proportional. They're going to have the same scale factor. So if we take a look at this one, where we would see that is the scale factor of a corresponding side on the image divided by the corresponding side of the pre-image is going to be the same for all the sides of the triangle. So here's what we're going to find is true. We're going to find that side, let's make this a little clearer. We're going to find that side A prime B prime, which comes off of our image, divided by the length of side AB, is going to be equal to the length of side B prime C prime over BC, and that's going to be equal to the length of side A prime C prime over the length of side AC. So you can see, class, this is actually proving that we've got a scale factor that's the same for every side of the pre-image and the image. That means that these ratios are going to have equal value. And if you take a look at this, you'll actually see this. If you do A prime B prime, that's 6. 6 over 3 is equal to 8 over 4, which is equal to 10 over 5. They're all exactly 2. So that means that our scale factor here is 2, and we know that these two triangles have corresponding sides that are proportional. Next one is corresponding sides are parallel. When you use dilation, you actually create parallel sides. That means the sides here, if we look at these sides, we know that AB, side AB, has to be parallel to side A prime B prime. And side BC, put a line over that, and then side BC is parallel to B prime C prime. And just like that, the other side as well, side AC is parallel to side A prime C prime. So dilation creates parallel corresponding sides. The next one is, interesting property, the distance from the center of dilation to a corresponding vertex is proportional. So not only are the corresponding sides proportional, but the distance to the center of dilation is also proportional. And that means we could write this statement and know that it is true. The distance from D, our center of dilation, to point A prime divided by the distance from D to A. So take a look at this. The distance from D to a vertex on our image divided by D to the distance to our pre-image corresponding vertex is actually equal to the distance to our next vertex on our image over that same vertex on our pre-image, and that's also equal to the distance from D to C prime divided by DC. So not only are the sides of our shape proportional, but the distances from the corresponding vertices to the center of dilation are also proportional. All right, last thing we know, that's number 5, last thing we know about dilation properties is number 6. The orientation of the image is the same as the pre-image. By orientation, we mean they're not reflected or rotated. If you take a look at these two shapes, they are turned exactly the same way. One of them didn't get flipped around counterclockwise or clockwise or get reflected vertically or horizontally. These two shapes are the same orientation. Okay, and the last thing I want to talk about here is this whole concept of scale factor to make sure you understand this. Okay, scale factor always has measurement from image or the copy on top and the pre-image or the original on bottom. Okay, so scale factor always has a measurement from the image from the copy here on top of your scale factor ratio, and the pre-image or the original measurement is always on bottom. So here's some examples of that. Let's write some examples. I'm going to do this in green. So let's say here's some examples of this. Now you can find scale factor all over this dilation, but here's some examples of that. I can look at a measurement from the image over the pre-image, and as long as those two things are corresponding, I'm going to get my scale factor. Let's take a look. I'm going to pick from my image or my copy, I'm going to pick the length of A prime B prime, and its corresponding side on my pre-image is A over B. So A prime B prime, that is actually 6. And AB is actually 3. We can simplify this to be 2 over 1. Divide top and bottom by 3, and we get 2 over 1. So our scale factor is actually 2 to 1. Let's take a look at another place. How about instead of looking at corresponding sides, we look at the distance to the center of dilations. Let's try that. I'm going to look at the distance from D to A prime. That's from the center of dilation to our image, and I'm going to look at that divided by the distance from the center of dilation to the corresponding vertex of our pre-image. So dA prime over dA. Well, D to A prime, be careful of this, D to A prime, that's 6 to get to here and 6 to get to here. So we have to actually add 6 together. So it's going to be 6 plus 6. There's the distance from D to A prime. And the distance from D to A on your diagram is just 6. Let's simplify that. We got 12 over 6. These are both divisible by 6. You're going to end up with 2 over 1, which is equal to a scale factor of 2 to 1. So you can see this scale factor shows up in actually lots of different ways. We can compare corresponding sides. We can compare the corresponding distance from the same vertices to the center of dilation. And both of those will get our scale factor. Now again, I want you to realize the image measurement or the copy measurement always goes on top. The number on the bottom is always from our original shape. If you get those flipped around, you're going to get a scale factor of 1 to 2, and that's actually reducing the shape. You can see in this case our pre-image got bigger. So this is a scale factor that shows an enlargement. If you flipped it around, you'd get a reduction, but we know it's not going that way. We're not going from this shape to this one. We're going from the pre-image to the image, and clearly that image is growing as we do the dilation. So there are your properties of a dilation.